Welcome back. So we talked about compression mechanisms and their impact on convergence, and we basically saw that if we were to integrate compression mechanisms in a simple algorithm like SGD, we can still establish convergence results. However, the dominant term depends on the properties of our compression mechanisms. And this is something that may not necessarily be ideal. We also saw that the biased compression mechanisms are generally better than the unbiased ones because basically at the cost of incurring a very small bias, the total compression error is going to be significantly smaller. So what we're going to talk about here is basically a way to modify SGD such that we mitigate the impact or the adverse impact of compression on the convergence. And to do that, we basically going to focus on biased compression mechanisms because, as we talked about before, they seem to be better than the unbiased ones in general. Okay, so let's assume that we have a biased compression mechanism that satisfies this property. Okay, essentially the total compression error is bounded by the norm of the quantity we are compressing a square times 1 minus some delta. Okay, and indeed we saw examples of mechanisms satisfying this condition: random dropout, random sparsification, and a scaled version of the random quantization strategy we talked about before. Okay, so what is delta here? Delta is basically our compression parameter. Okay, so it's something that is between 0 and 1, and if delta goes to 1, basically the compression error goes to 0. Okay, so we basically have low compression, or you could also say that we have a really good compression operator. On the other hand, when delta goes to 0, we have a high compression or a bad operator. Okay, and what we talked about in the previous video basically was can be described in this way: that A was so delta was basically something like A, or delta was equal to 1 over B. And what basically we saw was that the dominant term depends on 1 over delta. Okay, so that's what we saw earlier. So our goal here is to modify SGD to get a better dependence on 1 over delta. In particular, I want to basically make sure that this 1 over delta does not appear in the dominant term at all. Okay. All right, so that's our goal. And to do that, let's look at compression from a slightly different perspective. Okay, so when we are doing compression, we are basically throwing out a part of the information. Okay, now how about we don't throw it out? And let's take advantage of the fact that we have this repetitive process in learning, for instance, or in distributed learning. We are going to communicate for a certain number of communication rounds, not just one communication round. Okay, so therefore, instead of throwing the part of the information in this round, as we would do in regular SGD with compression, let's save what we are not communicating, and then maybe send it the next round. Okay, and let's repeat this process. Okay, so in particular, we want to save what we are not communicating in memory. Let's say we augment it somehow with the next message we would be sending, and then communicate that instead. Okay. So in some sense, if we are able to do this, we are communicating the information that we would be throwing out with some delay. Okay. So therefore, if I communicate long enough for, let's say, for an adequate number of communication round, therefore almost all of these pieces of information would be communicated to the receiver, but with some delay. And hopefully that delay is not too large, so therefore it's not going to be very detrimental to my convergence guarantees. Okay. So mathematically, this is what we want to do then. So let's say that E is some basically notion of what we would be throwing out. Okay. So what we want to do, therefore, we want to augment that with our message, compress that, and then send that to the receiver, instead of, let's say, just directly compressing XT and sending it away. Okay. So what is E? E is basically, again, what we would be throwing out, okay, or basically the compression error. Okay. So in this case, that I'm doing this augmentation, the error at time t plus 1, therefore, would be the difference between the full precision message minus what I would be communicating. Okay. So ET plus 1 is therefore is a compression error. XT plus E is the uncompressed message, and this quantity is C of XT plus ET is basically what we are communicating. Okay, so this is the idea that we want to basically utilize to modify SGD and therefore improve the dependence on the compression parameter. And this is basically something that's referred to as error feedback, because we are using this compression error as a feedback to guide what we want to send in the next communication round. Okay, and we can actually integrate this in SGD quite simply to get this error feedback SGD algorithm. So in particular, let's imagine that so we have some initialization W1. We also set the first compression error vector to be 0. And then we're gonna perform the following updates for capital T rounds. In each round, we're gonna generate a mini batch of samples. We're going to form the stochastic gradient. Okay. Now, in SGD with compression, we would be compressing this G and send it, let's say, to a server. Here instead, we're going to first augment our compression error, or a previous compression error with this gradient, and then compress that to form the message that we are about to send in this round. And therefore, we're also going to update the error and save it in memory. Okay. Once we do that, we send a message, and let's say the server performs like an update, first order update, such that it's going to update the parameters to go from WT to WT plus 1 by following the direction specified by the message MT. Okay, so this is called error feedback SGD, or SGD with error feedback. All right, so for this method, we can have the following theorem. So assume that the function is some potentially non-convex function, which is L smooth. And also assume that we have access to a stochastic first-order oracle, which again gives us an unbiased estimator of the true gradient with a variance that is bounded by sigma square. And also assume that the mini batches that we are generating and using in each iteration are statistically independent. Then, if we set the learning rate to be something like 1 over the square root of t, again, this is something that we would do in usual SGD as well. We can show that error feedback SGD can achieve the following result, that the error, the convergence error, has two terms, a dominant term and a higher order term. The dominant term is basically something like 1 over the square root of t, almost identical to what we had for SGD without compression. And notably, the dominant term is now independent of the compression parameter. In particular, here there is no appearance of 1 over delta. And 1 over delta appears in the higher order term, this term here. Okay? So therefore, we are sort of mitigating the adverse impact of compression by leveraging error feedback. And intuitively, this makes sense because, again, we are not throwing out information, we are communicating that with some delay, okay? Such that now this is more advantageous and again has less impact on the convergence. Nonetheless, it has some impact that only appears in the higher order term, okay? So therefore, better dependence on the compression parameter because as opposed to 1 over delta times the square root of t, here we only have 1 over the square root of t. All right. So we're not gonna go and prove this theorem in details, but I want to talk about the sketch of the proof, because again this follows the template we've talked about before, in the sense of studying the convergence of some virtual sequence and forming a potential function. Okay. So in particular, if you recall our discussion on decentralized SGD, we considered how the average model, which was a virtual sequence that it was not unknown to agents, would perform. Okay. Here we're also going to do the same thing. We are going to consider an idealized sequence with no compression error, and we want to see how does that perform, and then we're going to form a we're going to form a potential function that integrates the impact of compression, such that if we study its evolution, we'll be able to establish a convergence result for our algorithm. Okay. So what is our idealized sequence? It will be, as I mentioned, it will be something that is free of compression error. So in particular, we're going to define W tilde to be our idealized or virtual sequence, which is Wt minus eta times Et. In some sense, what I'm doing, I'm removing the compression error from my iterates Wt. Okay. So in particular, this is basically what we are doing. Okay. So therefore, given that I'm removing the compression error, this virtual sequence should be something that looks very similar to SGD without compression. Okay. Okay. So in particular, it should look something like this, where I go from the current W tilde to the next one by following the direction specified by the uncompressed stochastic gradient. Okay. Indeed, that's the case. Indeed, we can show that the way we define this virtual sequence is identical to define it in this way. Okay. How? It's very simple. So let's consider the next version of W tilde. Using this definition here, I can write this expression. Okay. Then I can use the definition of we can use the EFSGD's update, okay, to arrive here, and then finally we can use the basically the definition of the compression error, or the way that we would update the compression error to arrive here. So therefore, this basically is saying that the removal of the compression error from the iterates of EFSGD basically gives us the iterates of SGD without compression. So our virtual sequence that we are studying here is nothing but how SGD would perform. All right. So therefore, that's the sequence we're going to study. Also, again, this is maybe the fourth instance of this potential-based analysis we are talking about here. We have a problem where there is this important source of error impacting our convergence. So in the context of SGD with momentum, that source of error was the gradient estimation error. Or in the context of decentralized SGD, that source of error was the consensus error. Here, the source of error is the compression error. So we have to therefore study the evolution of the compression error through time and integrate that in our potential-based analysis. Okay? So therefore, we're going to consider and analyze the evolution of the compression error, and using the property of our algorithm and the assumption that our compression mechanism is a contraction, we'll be able to establish this recursive inequality that basically says that the next compression error is some constant that depends on the compression parameter times the current compression error plus some other terms, where this constant crucially is something that is between 0 and 1, thanks to the fact that we are using contraction. Okay. So again, this is something we've seen before, a recursive inequality having this form. So we define a potential function like this, where we look at the suboptimality of this virtual sequence plus how the compression error evolves over time. And we're going to study the evolution of the potential function by summing over its consecutive differences and leveraging our assumptions such as unbiased stochastic Wechsler oracle and the L smoothness of the function. And we'll be able to actually find a good constant CE here, given that this constant kappa is strictly less than 1. So therefore, given that we have this highly desirable form for our recursive inequality, we'll be able to actually utilize this potential-based analysis and ensure that our method, error feedback HCD, converges and enjoys this nice convergence property. All right, there you go. So this brings us to the end of our module on training algorithms and techniques, where we talk about advanced training algorithms, and we also talk about distributed learning paradigms. In the next module, we're going to talk about what I refer to as contextually constrained deep learning, where in addition to a performance-centric mindset, we want to make sure that some other criteria are also satisfied. With that, I'll conclude the lecture and I'll see you in our next video.